Hi guys, so this is 1.3 graphs of functions. We're going to be looking at whether a function is odd or even and what the graph of an odd or even function looks like. We'll also be evaluating graphs in this lesson. All right, let's look at it. So symmetry, when we're looking at symmetry, we're looking at a graph of a function can be odd, even, or neither. So here's the deal. If the function is even, this graph right here is even, you will see symmetry across the y-axis, which means if I fold on that blue line, that graph is going to match up. So this one is what the graph looks like for an even function. It's got to fold over the y-axis. Now, an odd function is going to be symmetric to the origin. So here is the middle, here's the origin. And so the symmetry is if this flips over the y and then flips over the x, then we know that the graph is odd. So in this picture, you can see symmetry over the origin, which makes the graph odd. Now, just so you know, if I had a parabola, and let's say the parabola is over here, and this looks like a terrible parabola, but you've got my point. This graph is neither because it is not folding over the y-axis and it's not folding over the origin. Now, another way to tell if a function is odd, even, or neither is to do the algebra test. So in order to do the algebra test, you're going to take x and replace it with the opposite of x. So this function, the algebra test would be y equals, and in place of x, I'm going to put the opposite of x squared, subtract 2. Now, you will notice that if you take the opposite of x and square it, this function is going to come out as y equals x squared subtract 2. Now, because this is exactly the same as the original, so here's the original function, and when I put in the opposite of x, here's the new function. And you can see that these are both exactly the same. If they end up exactly the same, then we know that the function is going to be even. So that is an example of an even function. So let's look at the example of an odd function. We're going to do the same thing, is we're going to take x and we're going to replace it with the opposite of x. So I have y equals the cubed root of x. The algebra test would be y equals the cubed root of the opposite of x. Now we know if we had a negative number under a cubed root, it's going to stay negative. So this is going to result in y equals the opposite of the cubed root of x. And so if your function ends up being the opposite of the original, so you can see here's the opposite of the original function. So here's the original, y equals the cubed root of x, and when I plugged in the opposite of x, I get y equals the opposite of the cubed root of x. So therefore, this is considered an odd function. So here's some problems we're going to try, and we're going to determine if the function is odd, even, or neither using the algebra test. So looking at example 1, we're going to take x and replace it with the opposite of x. So this would be, and I can just write y equals if you want. I have x, so I'm going to replace it with the opposite of x cubed, subtract 2 times the opposite of x. Then what you want to do is simplify. So when I take a negative and cube it, it's going to stay negative. And then a negative times a negative is a positive. So this gives me f of the opposite of x is equal to this. So let's compare it to the original function. So the original function is x cubed subtract 2. My new function is the opposite of x cubed plus 2. And you can see this is exactly opposite the original. This one's positive, this one's negative. This one's negative, this one's positive. Therefore, if it's exactly the opposite of the original, the function is odd. So this one is odd. You could graph it on your graphing calculator to verify that that function is going to have symmetry over the origin. Looking at B. So we're going to take g of x and we're going to find g of the opposite of x. This is going to give me 3 times the opposite of x to the 4th power plus the opposite of x squared. And I know this is a little bit abstract because we're not dealing with numbers, we're dealing with variables. But we know if I take this, the opposite of x to the 4th power, because 4 is an even exponent, it's going to come out the same as x to the 4th. So this would be 3x to the 4th, and the same thing with the square is going to come out as x squared. Now you can see that when I compare this to the original, you can see that it comes out exactly the same. So therefore, B is going to be even. All right, let's look at C. So C, I'm going to take g of the opposite of x, which is going to equal 4 times the opposite of x subtract the opposite of x, ooh, I'm out of room, absolute value of 4 times the opposite of x. All right, so 4 times a negative x, if it's negative, and that's why I just keep saying opposite, because if x were a negative number, then it would be positive. But anyway, so 4 times the opposite of x is the opposite of 4x. And these two are going to make it plus x. And then we have the absolute value. And this is going to come out the same as 4x. And so now what we're going to do is we're going to compare this to the original. Here's the original, and here is my new one. And this was positive, this is negative, this is negative, this is positive. And so our function has to be odd again. So this one is the same as example 1a, it's odd. All right, let's look at example 2. So looking at example 2a, if I do g of the opposite of x, it's equal to the absolute value of the opposite of x plus 3. Absolute value is going to give me the same thing as the absolute value of x, plus 3. You can see that my two functions are identical. This one and this one are exactly the same, and so we know that the function is even. This one right here is a little bit different than C. So let's go ahead and give it a try. So we have f of the opposite of x is equal to 4 times the opposite of x times the absolute value of the opposite of x plus the opposite of x squared. So this is equal to the opposite of 4x. This absolute value will come out the same as just x. And then a negative times a negative is a positive. So this one is going to be plus x squared. If we take this and we compare it to the original, here's the original here, and you can see this is the opposite, but this part of the original is the same. So since it's not the opposite of both parts, both terms, we know that this one is going to be neither. All right, and then the last one is C. If I take -2 times the opposite of x over 3 times the opposite of x squared. -2 and -x is going to give me 2x on top. And then you can see that when I take this negative and I square it, it's just going to come out as 3x squared. Now, this negative you could pull out in front. And so really, the original and the new one are exactly the opposite of each other, because this negative you could pull in front, so it's opposite of that. And so we know that it's going to be odd. All right, that's odd, even, and neither functions. So now what we're going to do is look at extrema. So relative extrema is going to be your maxima or minimas, and those are your hills or your dips. So this is a maxima relative, and this is a relative minima. Now, I couldn't see these points, so I just estimated, but I think this is at 0 up 2, and this is maybe right, if that's a 2, it'd be right 2.5, and then down -5 if this counts -2, -4, -5. And again, I'm just estimating because I can't really see the numbers. So what we're going to do with relative extrema is this. Alex is going to ask you for all values at which f has a local maxima. Alex is asking you for the x value here. So the first one is the x value. Here is a local maxima, and the x value is at 0. So you could put x equals 0 or 0. And then all local maximum values of f. This one is asking you for the y value, and this is going to be on the Alex homework and the Alex test. So now it's asking you for the y value, and the y value is 2. So the answer would be 2 there. So that is maximums. Now minimums would be here. So if it asked you for the local minimum, then you would put a 2.5 for the first question and a -5 for the second question. All right, absolute extrema. So absolute extrema is where we are moving to the left forever. As this is moving down, it's moving left forever. And as this is moving up, it's moving right forever. And so the domain, which is left to right, is going to be -infinity to infinity. Now looking at increasing, decreasing. So increasing, if you're on a roller coaster and you're going from left to right, then you're increasing when you're moving up. So increasing, this whole part of the graph is increasing. And then decreasing is when we're moving down from left to right. So here's the decrease. Ooh, looking terrible. Decrease. And then the increase is going to be where it turns again and the roller coaster moves up. Now, increasing and decreasing, what's important to know is you always use the domain. So we're looking over the x values. So this is all the way out here on the left, and it's moving, increasing, increasing, increasing till it hits right here. And so the increase part would be -infinity until we get to, let's say that that's exactly at when x is -3. So there's your increase. Your decrease is going to be x values again, but it's going to be where you start here. So the x value at -3, and it ends here, and the x value is 2. So the decrease is going to go from -3 to +2. And then the increase is going to go from where we turn again. So pick 2, and let's increase all the way. This is moving to the right forever. So let's increase all the way to infinity. Now, I would recommend just using parentheses for all the turns. Some books will use brackets where you turn, but you don't need to. Just use parentheses. So in this example, just like you read a book from left to right, you're going to read your graph from left to right. And so let's look at increase and decrease. So if I'm supposed to highlight the decreasing in this graph, and I think I want to do the blue. Let's redo that. From here to here, it decreases, and then we have an increase, a constant, and a decrease. Looking at the next graph, we have a increase. So we're looking for increase, and the increase is going to increase as it moves up, and there's your increase. The constant is when we go straight across, and so the constant in the graph is going to be from here to here. Now, increase, decrease, and constant, when you write it in interval notation, you always use the x values. So decreasing, it decreases from -5 to -3. And then it also decreases from when x is 4 to when x is 6. 4 to 6. So make sure you use the domain. Use x's for increase, decrease. It's increasing from -3 to 0. And here it's constant from 0 to 4. Again, you can use parentheses for interval notation for everything. So in a constant function, you get no change in the y values as the x values increase. So it's just, think of a constant speed. You go straight across. Looking at boundedness, we use boundedness in calculus. So how we find if something is bounded is it would be like drawing a horizontal line above and a horizontal line below. And if you can box the graph in from above and below, then the graph is considered bounded. So this last picture here is a bounded graph. Now, if you have a graph that looks like this, where it has a very low point, but as we move here, it's going to be moving up forever, then we call this bounded below. And so you have a low point, but no high point that's bounded. If you have a graph that has a very high point, so it's above, you can say it's bounded above, but at the bottom part, the graph goes down forever. The only graph that's considered completely bounded is when it's bounded both above and bounded below. So you box the graph in and then it's bounded. So this graph is called the greatest integer function, or a piecewise graph. It is not continuous because if I were drawing these steps or tracing the steps, I have to lift my pencil up every time I hit a new integer. So for example, you have x is 0, 0, 0, 0, and then when I hit the bigger integer, I go up to 1. It's kind of like your birthday. You're 1, you're 1, you're 1, you're 1, all the way until you turn 2, open circle, and then you jump up to 2. You're 2, you're 2, you're 2, you're 2, all the way till you turn 3, and then you jump up to the next step. So the greatest integer function is going to be symbolized with these double brackets. So it's a double bracket. And what you're going to do is you're always going to go to the left on the number line when you do this when you find the greatest integer. So for example, if I'm looking for f of 1/3 and it's a greatest integer function and I want to evaluate, then what I would do is on a number line, here's 0, here's 1, and here's 1/3. Now, you're looking for the closest integer to the left, all right? So it always goes smaller, just like you're not 17 until your birthday. So even if you're 16 and 11 months, you're still 16 until you turn 17. So you always go back to the left on the number line. So if this is f of 1/3 and it's a greatest integer function, then if I come to the left, the integer to the left is 0. F of pi. So pi is 3.14 if I'm going to estimate it. So if we look at pi on a graph, here is 3 and here is 4 and here is pi. So the greatest integer is going to be 3 for the greatest integer function. So 3. F of -3. So if we're on the number line again, and here's 0, and here's -3, and I'm asking you for the integer, then your answer is just the integer. So this is going to be -3. F of -9.2. So this is the one that a lot of students miss. So here's -5, and here's -10, and here's -9.2. While -9.2 is closer to -9, if I'm evaluating the greatest integer function, then it's going to be to the left, which is -10. So you always go smaller. So this is -10. This is what the greatest integer function graph looks like. If you wanted to, you could set up a table and you could plug in numbers to get this function. So y equals the greatest integer of x. If I put in 0, then my answer would be 0 for my output. If I put in a half, my answer is also 0. If I put in 3/4, my answer is 0 for the output. And this is here. So you're 0, 0. You're a half, you're still at 0. You're at 0.75, you're still at 0. You're at 0.99999, you're still at 0. All the way until I hit 1. And then y would be 1, and I would jump up to 1. All right? If I had 1.5, I would go to 1. So this is right 1.5 and up 1. All the way until I get to 2. So then when x is 2, y would also be 2. So example 4, we're going to look at the graph of the greatest integer function. F of x equals the greatest integer of x plus 2. So this is a typo here. Cross off that S. All right, so here we go. So you're going to take a table. And let's talk about greatest integer. So if I plug in 0, then that is the greatest integer of 0 is 0. So this would be 0 plus 2, which equals 2. So 0, we're up 2. 0, up 1, 2. If I plug in a half, the greatest integer of 0.5 plus 2, you go to the left, so this would be 0, left to the nearest, or left to the integer, so 0 plus 2, which equals 2. So at a half, you're also up 2. If it were 0.75, you would go back to 0 plus 2, which is also up 2. And you're going to do that all the way until you get to 1. 1, the greatest integer of 1 plus 2 is going to equal 1 plus 2, which equals 3. So when we go right 1, we're up 1, 2, 3. I like to just test decimals. If I were to put in 1.5, the greatest integer of 1.5 plus 2 is, this goes back to 1, so 1 plus 2 is equal to 3. So you would be right 1.5 and up 3. And you're going to be that way all the way here until you get to 2. When x is 2, then you would have 2 plus 2 is 4. So right 2 and up 4. And you can see the pattern. So the table kind of helps you with the pattern. And then what you can do is you can just fill in the pattern. All right, making sure you start with the closed and then you open on the right-hand side. And so here is your step pattern, and there's your step graph. Example number 5 is a piecewise function, and we're going to graph each piece using a table. So the first piece is f of x, or y, is equal to x. X is greater than or equal to 0. So you start with 0, and 0 is going to be closed on that point because of the equal to. Here's the equal to, right? So if I plug in 0 for x, I get 0 for y. If I plug in, I want to go greater than, so if I plug in 1, I get 1. If I plug in 2, I get 2. And so this part of the graph is 0, 0, right 1, up 1, right 2, up 2. And if I wanted to continue the pattern, it would be like this. So here is the first piece of the graph. Now let's look at the second piece. So the second piece is y equals the opposite of x, and this says x is less than 0. So it would be an open circle where you start, and even though it says less than 0, you want to start with 0. It's just, it would be an open circle here, all right? And then you would, if you plug in 0, the opposite of 0 is 0. If you plug in, go smaller, since it says less than 0. If you plug in -1, the opposite of -1 is 1. So it's left 1, up 1. The opposite of -2 is 2. And so this is going to continue. And you should recognize this function. This function is the absolute value function. So this is the absolute value function. And here's what the piecewise graph looks like. This one is f of x equals cosine x. And so what I would recommend is, if you remember what the cosine graph looks like, we're going to start at 0, but because it doesn't say equal to, we're going to have an open circle. So here, remember, the cosine graph starts up at 1, and then your cosine graph is going to go here, and then down to -1, and the cosine graph just keeps moving like that. So there's your cosine graph. And then the second piece is going to be a parabola. So your parabola is x squared subtract 2. You could use tables for both of these. If you remember that x squared is a parabola, and -2 is going to shift it down 1, 2. So here's your graph. Because we're including 0, it would be a closed circle here. And then it's right 1, up 1, right 1, up 1, 2, 3, and then right 1, up 5. And so here is the piece that is the parabola. We call this discontinuous because there's a jump right here. So it is considered a function, but there is a jump at when x is 0. So you can put discontinuity at x equals 0. Example 7 is also a piecewise graph, and you are going to start with y equals the opposite of x squared. Now, if you know what that function looks like, you can graph it, or you can use a table. If you use a table, it says x is greater than or equal to 1, so you're actually going to start with 1, and at that point, you're going to put a closed circle. So the opposite of 1 squared, you would square the 1 first and then bring the negative in front, so it equals -1. So you would go right 1 and down 1, and you would put a closed circle there. Now we're going to try anything greater than. So let's go to 2. If you take the opposite of 2 squared, you're going to get 2 squared is 4, and the opposite of that is -4. So you're going to go right 2 and down 1, 2, 3, 4. Because I know this is a parabola, this graph is going to have a little bit of curve to it. So if you can kind of draw the piece of the parabola there. All right, let's go to the line. This is linear. Now it says it's less than 1. You want to start at 1 and then just use an open circle because we don't include 1, but we still want to start at it. All right, so 3 times 1 is 3, and 3 plus 2 is 5. So this graph starts at right 1 and up 5. 1, 2, 3, 4, 5. If I put in something smaller, see how it says x is less than. Let's do 0. 0 is going to give me 2. If I plug in -1, I get -3 plus 2, which is -1. So left 1, down 1. And -2 is -6 plus 2 is -4. And then you would use a straight edge. And I made a mistake on this. This is open. So that circle here is supposed to be open. This is open here. There we go. Now it looks great. And then what you would do is you just use your straight edge. And it's hard for me to do it with this pen, but there's your piecewise graph. So this graph is a rational function. Here is the function, and it has 2 asymptotes. It has a vertical asymptote right here. Ooh, ugly. Vertical asymptote right here at 2, and it has a horizontal asymptote right here at 1. And so what we're going to do is let's talk about domain. This goes left forever and right forever, except for x can't be 2. So it's going to be all real numbers except for when x is 2. So let's write that as -infinity to 2, don't include 2, and 2 to infinity. All right, the range goes from low to high. So this goes down forever and then up forever, except for y cannot be 1. And so the range is going to go from -infinity until we get to 1, and then from 1 up to infinity. This graph is not continuous, and how we know it's not continuous is we have to lift up our pencil in order to graph the whole thing. This graph, when we say symmetry, we're talking about is it odd, even, or neither. And so for symmetry, we're going to put none. For boundedness, it goes down forever and up forever. So this graph is not bounded. Remember, bounded, it has to be stuck in a box in between 2 horizontal lines. Extrema is going to be these end values. So the extrema, this right here is moving left forever. So how we write the extrema is we write the limit as x approaches negative infinity, and then you would write f of x is moving towards 1, so it would equal 1. Over here, we have the limit as x approaches positive infinity. F of x is also approaching 1. All right, so those are your two extremas. Asymptotes. There's a vertical asymptote at x equals 2, and there's a horizontal asymptote at y equals 1. So that's everything. I need you to do the U-try on your own, and then also make sure that you don't forget to do the reflection. So thanks everyone. Have a fabulous day, and I'll see you soon.